So we are going to prove this theorem that Sn, composition is a group where Sn is the set of all permutations and symbols, and this looks like O is the composition of mappings. Okay, so what we have to show? We have to show that Sn is a group. Okay, so we must prove the 4 necessary conditions for a set to be. What are the conditions? We will take one by one all the 4 conditions. The first one is G1. Okay, G1. So what is the property G1? G1 is the property which says that the operation composition, this one, is a binary operation. On Sn. Binary operation means the Sn is closed with respect to this operation composition. Okay, so the first property is composition is a binary operation on Sn. Okay, so actually we have to show the closeness of this composition in this set Sn. So we take 2 elements of Sn and we show that their composition is again an element of Sn. So take 2 elements, for example, say F and G. F and G are 2 elements of Sn, and what we have to show? We must show that their composition means F composition G is also an element of Sn. So let us prove this one. So this composition will be an element of Sn if it is a permutation, because Sn is the set of all permutations of n symbols. So for our convenience, suppose we denote the set of n symbols by S. What is S? It is the set of n symbols. And you can take these symbols, for example, A1, A2, A3, and so on, An, or you may take 1, 2, 3, 4, to n, whatever you want. Okay, it doesn't matter because these are just symbols. So to show that F composition G is again an element of Sn, we have to show that F composition G is a permutation on n symbols. Permutation means a 1-1 and onto mapping. So we show it one by one. First we show that this composition is a 1-1 mapping. Okay, so to prove this, what we have to show? We have to show that if I have composition G of some element x 1 is equal to F composition G of some element x2 for some x1, x2 belongs to the set of n symbols, then these two elements means x1 and x2 must be equal. So let us show this. Then look here, f composition g of x1 is equal to f composition g of x2. What it means? By the definition of composition, it means f composition g of x1 means it will be g of f of x1, and f composition g of x2 means g of f of x2. So now if you remember, this G is an element of Sn. It means G is a permutation. It means G is 1 1 and n2 both. So because G is 1 1, G is 1 1, what it means? For your convenience, you can just suppose this f of x1 is y1 and f of x2 is y2. Okay, y1 is assumed this value and y2 is assumed this value. So since G is 1 1, therefore if elements of image of two elements y1 and y2 under G are equal, then y1 and y2 must be equal. Okay, why? Because G is 1. Okay, so y1 means f of x1 and y2 means f of x2. Now what it means? It means you are getting the images of x1 and x2 are equal under the mapping F. So what it means? It means these 2 points, these 2 elements must be equal. Why? Because F is also 1. So ultimately what we get? We get this. If f composition g of x1 is equal to f composition of x2, it implies that x1 is equal to x2, and therefore the composition must be 1. Okay, so it is the first property which we have. Now the second one. Second, f composition g is onto. Okay, we have to prove both these, 1 1 and onto. Only then this composition will be an element of Sn. So for ontoness, what we have to show? Simple. We have to show that every element of S means set of n symbols. So if Z is an element, any arbitrary element of S, then there must be some X in S such that Z is equal to f composition g of x. Okay, so what we have to do? We have to do this one. If Z is an element of S, then we have to search, we have to find an element X of S such that the image of this X under F composition G is Z. Okay, so let us search this X. How we will search? Simple. We shall use the properties of F and G, obviously. Okay, so if you remember, G is an element of Sn. It means G is 1 1 and onto. So G is onto, and therefore for this Z belongs to S, there exists can write here, since G belongs to Sn, that is G is onto, there exists an element Y in S such that the image of G image of Y must be equal to Z. Okay. Again, now we are going to use the ontoness of F. Here we have used the ontoness of G. Now we are going to use ontoness of F. So since this Y belongs to S, so there exists some X belongs to S such that this Y is equal to the F image of X. Okay. So ultimately we have found this X, which was our goal. Okay, so ultimately what we get this one, Z is equal to, now Z is equal to what is the value of Z? It is Gy. Okay, now substitute the value of Y. What is Y? Y is nothing but F of X. Okay, and what is G of F of X? By the definition of composition, it is nothing but F composition G of X. So ultimately, for given Z belongs to S, we can find an X belongs to S such that the image of X under F composition G is Z. So it shows that the mapping F composition G is onto as well. Okay, so thus F composition G is 1 1 1 2. Okay, and so this must be an element of Sn. Okay, so this proves that the operation composition is a binary operation on Sn. Okay, so we have proved the property G1. Now we go to G2. What is G2? You know, G2 is the associativity. Okay, associativity of composition of matrix. For associativity, we have to take three elements of Sn. So I take namely F, G and H from Sn, and for associativity we must show that F composition G composition H is equal to F composition G composition H. Okay, so we have to prove this one. Okay, so let us prove. How we will prove? Suppose X be an arbitrary element of S. Now if these two mappings, this one and this one, result same when applying on X, then we say that these two mappings are equal. So we have what we have to show? We have to show this one. F composition G composition H of X is equal to F composition G composition H of X. Okay, this one is our goal. We have to prove this one. So let us prove. Before starting the proof, for your convenience, I am supposing this F composition G as capital F and this G composition H as capital G. Okay, so what we have to show? Now we have to show this one. F composition G means capital F composition H of X is equal to F composition capital G. We have to show this one. So let us go. So we start with LHS. What is LHS? It is F composition H of X. Simply apply the definition of composition, we will get H capital F of X. And what is this? It is H. Substitute the value of capital F. Capital F was F composition G. Okay. Now, what is F composition G? According to definition, it is G of F of X. Okay. Say it is equation number 1. Okay. Now, consider the RHS. RHS was F composition capital G. Okay. So, as usual, the definition of composition, it will be equal to Z and F of X. Okay. So, what is G? G is G composition H of F of X. So if you are not comfortable, you can assume this F of X as Y. So I write here Y is nothing but it is F of X. Okay. So solve it. Again apply the definition of composition. You will get G composition H of Y is nothing but H G of Y is equal to H G of Y. Y means Y is nothing but F of X, so it is F of X. Okay, say it is equation 2. Now you can see from equation 1 and 2, if you look here, this is the value of capital F composition H of X, this one, and this one is the value of F composition capital G. You can see these two values are same, equal. So what it means? It means we have shown this one, that is this one. And it was our goal, and this from 1 and 2, we'll write like this. From 1 and 2, we have F composition G composition H of X is equal to F composition of G composition H of X for all X belongs to S, and this shows that these two are equal. Okay. And it is what we want. So associativity is not true. Okay. So let us move to the third property, G3. What is G3? Third property, third necessary condition for a set to be true. It is the existence of identity. Okay. So most obvious is the answer of this. Identity mapping. Identity mapping, as you know that identity mapping behaves like the identity for the composition of matrix. So most obvious answer to this search of existence of identity is the identity mapping. But identity mapping will be the identity of Sn with respect to composition if this identity belongs to Sn. Okay, so we have to check the identity mapping belongs to Sn or not. So identity mapping is the mapping which defines from S into S, and it defines like this. that I of x is equal to x for all x belongs to x. For all x belongs to x. It is our identity mapping. As we all know that the identity mapping is a 1-1 and onto mapping. Okay. So I, that is identity mapping, is 1-1 and onto. Therefore, this I must belongs to Sn, because it is 1-1 and onto, that is it is permutation. So it must belong to Sn. Now we check formally that this identity mapping is actually identity or not. So for this we have to check this one. These two must be equal to f. If we show this, then it means I is the identity of Sn. So proof is very simple. Let us show this one like this. Suppose x is an arbitrary element of S. Then what will be the value of I composition f of x? Again, by the definition of composition, it will be equal to I f of I of x, because I is the identity mapping. So ix must be equal to x, and this one, what this implies? What it means? It means I composition f of x is equal to f of x for all x belongs to S. So it means these two mappings, I composition f and f, effect results same when applying on an element of S, and therefore these two are equal. Okay. Similarly, you can show that this one is again equal to f, and so it concludes that this I must be the identity of Sn. Okay, so we have shown that Sn consists an identity element for the composition of mappings. Okay, so to the third property, now let us move to the fourth one, G4. So what is G4? G4 is the existence of inverse. Okay, so existence of inverse. But what it means? It means if f is a permutation, that is f belongs to Sn, then there must be an element. We will represent this element by f inverse in Sn such that the composition of f and f inverse, or f inverse and f, must be equal to the identity element I of Sn. Okay, we have to find this f inverse. So now how we will find? Most obvious and natural answer of this question is from set theory, and it tells us that this mapping which we are searching for, f inverse, should be the inverse mapping of f, which we already studied in set theory. What is inverse mapping? If we for some x belongs to S, suppose y is equal to f of x. Okay, then we define inverse mapping like this. So x is equal to f inverse y. If y is equal to f of x, then x is equal to f inverse y. But the question is that can we define the inverse mapping like this? If we define inverse mapping like this, then whether it is well defined or not, that is the question. So Answer is again from set theory, which you already studied in the lower classes. Because F belongs to Sn, it means F, what is F? F is a one-to-one onto mapping. Because F is 1 onto, therefore its inverse must be exist. So existence of inverse is solved. Okay. Now our purpose, our goal is that we have to show this inverse is in Sn. It is not outside of Sn. It belongs to Sn. That is our goal. We have to show F inverse belongs to Sn. What it means? It means yes, F inverse exists. F inverse exists by set theory. But question is that whether it belongs to Sn or not. So we have to show that it belongs to Sn. Okay. And now when will F inverse, this F inverse will belong to Sn? The answer is if F inverse is a permutation. Permutation means if F inverse is 1, 1 and 1, 2. So let us see whether it is 1, 1 and 1, 2 or not. So the first one which we want to show that F inverse is 1, 1. So how we show this? Answer is simple. 1, 1. 1, 1 means if we take two elements y1 and y2 in S, and suppose F inverse y1 is equal to F inverse y2, then we must show that y1 is equal to y2. Okay, so it is our goal. Clear? So suppose y1 and y2 belongs to S. Then we use the ontoness of F. F is onto. So we must have two elements. There exist two elements x1 and x2 in S such that y1 is equal to f of x1 and y2 is equal to f of x2. We can write this because f is onto. Okay. Now suppose f inverse. Suppose f inverse of y1 is equal to f inverse of y2. Okay. So what it means? F inverse of y1. So if you see here, y1 is equal to f of x1. Therefore, f inverse of y1 must be equal to x1. Similarly, y2 is equal to f of x2. So f inverse y2 must be equal to x2. Okay. Now apply mapping f on both sides because x1 and x2 are equal. Therefore, their images must be equal. Okay. This property, you can say this property comes from the well-definedness of it. Okay? So f of x1, what is f of x1? Is nothing but y1, and what is f of x2? It is y2. So what we have shown? We have shown that if f inverse y1 is equal to f inverse y2, then y1 and y2 must be equal, and that is exactly what we want to show. So thus we have shown that f inverse is 1, 1. Now let us come to the second one. F inverse is onto. How you will show? Again, answer is simple. For ontoness, we have to show if x is some element of S. Okay, then there must be some y in S such that this x is an image of y under the mapping F inverse. If you can prove this, then we show that F inverse is onto. So let us assume that x belongs to S, be any arbitrary element. Okay. Note that this mapping F belongs to Sn. mapping F belongs to Sn. What it means? It means F is a mapping from S to S, which is 1 1 and on 2. Okay, since mapping is from S to S and X belongs to S, it implies that the image of X under F will be an element of S. Okay, so this name this f of x as y. Say y is equal to f of x. Okay, so this is the y which we are searching for. Hence, y is equal to f of x, and you can see this y is an element of x. And by definition of inverse mapping, if y is equal to f of x, then this x must be equal to f inverse of y, and it is what we want to do. Okay, so what we have shown that if x is an element of s, then we can find a y which is actually the image of f image of x, such that the inverse image of y is x. So it shows that f inverse is onto, and since f inverse is 1 1 and onto as well, therefore f inverse is a permutation and so belongs to Sn. Yes, it is what we want to prove. So thus we have shown that all the properties G1, G2 and G4 are satisfied for Sn composition. So it shows that this is a group. Okay, it is a group. So next task is that show that this group Sn composition is non-abelian. Okay, so we will see later that this group is not abelian, it is non-abelian. Okay, so let us conclude this lecture for now. We'll meet again in next lecture.